All right. It's almost 4 o'clock, so I can get started. Hello, everyone. Um, my name is Anirudh. I'm a data scientist at Databricks. So today I'll be presenting on this topic on how we are using AI to prioritize vulnerabilities. So here we're going to talk about an automated workflow for tagging important software vulnerabilities. So just a few definitions. I think people over here might be knowing it, but just to rephrase, CVE is a weakness or a flaw in a system or a software that could be exploited by attackers, right? And there are a couple of scoring systems out there which actually give some scores on those vulnerabilities. CVSS is a common vulnerability scoring system which assigns a score to a vulnerability based on its severity. And EPSS is another system that assigns a score based on the likelihood of it being exploited in the wild, right? And there are a few scanners, vulnerability scanners, which actually help to kind of report vulnerabilities within your infrastructure. Trivy is one of the software which basically detects and reports vulnerabilities within the software packages or dependencies that they contain. And Qualys is another vulnerability scanner that identifies vulnerabilities in organizations' operating systems and databases, right? So these are some of the definitions just to get a recap of what vulnerabilities are, right? So why do we need to prioritize vulnerabilities? If you see this plot, you can see the number of vulnerabilities that are published every day. They keep increasing. From 2009 to 2023, like as you can see the plot, it's been growing exponentially. And security teams can't really respond to each and every vulnerability, right? And we don't know like which of these is important for our infrastructure. Like there could be some things that are important for Databricks, others might be important for Adobe, or like if you're looking at Tesla, there could be Tesla-related software vulnerabilities that Tesla needs to care about, right? So every organization needs to only look at subset of vulnerabilities, and there's a lot of unstructured data out there, and we need to understand how to process this data and only look at the ones that are relevant to our infrastructure, right? So for that, what we did is we developed an AI-based system to proactively identify, categorize, and rank vulnerabilities, right? There are different steps in this process. As I've outlined, there's a CVE ingestion process where we ingest CVE from different data sources, and there's also a product or a library extractor, which from the unstructured data, we extract what libraries it is affecting, right? And there's a scoring system, and we also create tickets based on that. So there's a high-level overview of that. I'll go into the details of each one of them. So how do you define an important CVE, right? Like as I mentioned, CVEs have these scores, but CVEs with high scores that are published that are typically critical to the world, right? But there are also some CVEs that are critical only to your Databricks, and there are some CVEs which are critical to world and Databricks, right? That's what we are kind of focusing on this part. Like this is what we are more interested in, the ones that are critical to the world and also are within Databricks. So those are the ones that we should really care about and we should really patch first. So there's a high-level flow of how this works. We first ingest data from all CVE data from using an API from all the databases. There are Intel Strobes database, there's a GitHub advisory database which kind of publishes CVEs on a daily basis, and there's something called CVE Shield database, so we extract from them. And also the other thing is we also ingest blogs and news articles. RSS feeds, like there could be something on Twitter that is like trending and saying that, oh, this vulnerability everyone is affected by this, or also news articles might be talking about it. So we want to actually get to those faster, like as and when people are talking about them, we need to be able to identify them faster, right? Because before any damage is done, we should be able to identify them. And then we do an ETL of them, and then we generate some features. One of the features that we generate out of them is the library extractor, where we extract the library from the CVE, and we compare it with our libraries within Databricks using a vector search to find out which are the similar libraries that are related to that library. And then once we do that, we also need to identify out of all the similar libraries, not everything might be like there could be some errors in the way similarity is calculated. So we need to identify which are the most vulnerable libraries among this subset of similar libraries. And then once we have these libraries, we map it to our services, and based on how important the services are, we score those CVEs. And then we aggregate scores, and then we identify the critical CVEs and create tickets based on those CVEs, right? So there's the high-level workflow of how the process works. So these are the various places where we're ingesting data from. There's an API for Intel Stropes. Also, there's a GitHub advisory database, and there is a CVE Shield database which publishes like CVEs on a regular basis, on a daily basis. It has a dashboard which says what the CVE is and things like that, right? And also we're getting it from RSS feeds like news and blogs and security blogs. We ingest those RSS feeds as well. So how does a typical CVE information look like, the ones that are published in the databases, right? So there is something called a CVE number, this is the year the CVE is published. And there's also a unique ID specific to the vulnerability, right? And there's also a description which kind of says, okay, this is Apache Lab4j vulnerability, and it was affected by these releases, and so on and so on. So there's a lot of text out there. And there's also these are the scores that, as I mentioned, right? Like there's a CVSS score, there's a base score, and also there is some advisories like which have referenced the CVE and things like that. So these are all the information that we are basically using as an input for our model. Once we have that, we need to generate the features, right? So these are the features that we then generate for each CVE. What is the CVE ID? What is the title? What is the description? And there's also severity based on what the world thinks, whether it's medium, high, or critical, and number of references for the CVE. And these are some scores: exploitability score, impact score, whether there's a patch available for the CVE, whether it can be exploited or not, and whether it's seen in the wild, whether it's trending in Twitter and things like that, right? And what is the library, what is the age of CVE, and the date it was published and things like that, right? So these are all the information features that we're extracting from that unstructured data, right, the text data. So to extract this information, we actually leverage LLMs to extract these affected software packages name from the description of the vulnerability, right? So given the CVE, we need to know that the package over here is pkgconf, right? This is from structured data, maybe it's already there, but if it's not there, we need to pass this to an LLM and say, what is the library that you're talking about over here that is affected, right? So that's the first prompt that we kind of ask an LLM to get this information from this text, right? So what we have seen is LLMs have been trained on this data before, or they have this knowledge, so they're able to identify that this is the library that's being affected given a text, right? So it automatically says, oh, pkgconfig or bzip3 or mark it down itpy. So this is the one that is getting affected. That's what the CVE is talking about, right? So once we have extracted that library from the CVE, we need to match that to the Databricks packages. So why is that important to match to Databricks packages, right? First, we need to understand dependencies between different software packages. For example, a vulnerability in IPython does not necessarily affect CPython, but a vulnerability in CPython may affect IPython. So, for example, if we say, okay, if there's IPython, find all the similar libraries in my environment that are similar to IPython. If you're doing a semantics search or like a string-based matching, it will say CPython is very similar to IPython. But we should also know that a vulnerability in IPython does not affect CPython. So this kind of knowledge is not there just by doing a similarity search. So this is the additional knowledge that we have to, that LLM actually gives us, right? If you can train an LLM, then it can learn that these dependencies are important, right? And also account for variations in the characteristics of software packages. Characters of software packages, like scikit-learn, with a hyphen, or scikit-learn, or sklearn, pysklearn, all this might be the same. So there are some variations. Or we also need to account for version-specific vulnerabilities. So OpenSSL 1.01 to 1.01F may be vulnerable, but anything beyond that, G to 1. May include patches that address the vulnerability, right? So if we have something greater than that, then we don't, in our environment, we don't have to worry about that. So there are all this information that need to be fed into the LLM to get the right results. So on a high level, how are we doing matching, right? First, whenever we get a library or a package name, this is extracted from the description of the CV. We do a vector similarity search, and we get maybe top 5 or 10 packages which are most similar to that CV. Once we have this, then we prompt the LLM to say which are the most vulnerable packages. Like as I mentioned, the similarity might have, like if there's IPython, it could have said the related Databricks packages is CPython. But after this step, it will say, okay, even though CPython is similar, but CPython is not vulnerable. So it would eliminate this at this step, right? So these are the different steps. So how did we improve the LLM accuracy, right? By integrating powerful these language models, we can improve the software matching process. We tested a couple of models and experimented with various methods of improving the LLM performance. So I'm going to talk about some of the methods, which is automated instruction optimization and fine-tuning. So what is automated instruction optimization? The idea is first you start with some prompt, but we are asking other LLM to correct the prompt by itself, right? So for example, given that there's a vulnerability scanner, this is the initial instruction and this is the desired format of the output. But there is much more in the prompt that you could add over there, right? So what we say is first you give that instruction and the data set and a labeled data set, like a ground truth data set to that model. And then we basically, based on this initial prompt, we evaluate how good is our matching, right? And then we kind of get the errors on this ground truth data set. But we ask another LLM to basically refine your prompt in the next iteration so that you get a better accuracy. We keep repeat. Now we have the new instruction and we again provide the ground truth data set until we reach a specific accuracy which we are comfortable with. We keep repeating the steps. Like you could say a threshold, like the accuracy has to be this much in your ground truth data set. So that's how you kind of refine the prompt. And we found that the way the prompt is, the wording of the prompt affects the output of the model. Sometimes even bullets or highlighting something or making something bold, that also was actually changing the accuracy. So that's how we kind of tried to use another LLM to make sure what prompt can we get, right? Which is the optimum prompt we have to use for this model. So this was the final instruction, right? As you can see, it numbered it, and there were some things that were bold. I think it feels like bolding some things might be important, and those are some things that we kind of don't pay attention to, but I think it's important from a semantic and words perspective that LLM has to focus on these things. The other approach that we used is fine-tuning. As I mentioned, fine-tuning is basically making your LLM specific to your data, right? You could take an LLM that is trained on maybe code, right? But you have to be able to tune it to your particular environment. Like your code might be different compared to the code out there in the universe. So what you do is basically we fine-tune few layers of those LLMs based on your target data set. And then, and again train from scratch. So this is what is fine-tuning. So we actually employed these two techniques to improve the performance of our large language model. So there is some. These are some of the numbers that we saw for fine-tuning. We used a data set of 300 samples, where each row includes, like, we got a ground truth data set. We asked our security team to basically provide us a ground truth data set. So the data set looks something like this. So I have this package, and I have these similar packages, and the most vulnerable package is this, right? So those are the 3 rows. Three columns in the data set, and there were around 300 rows. So we use the ground truth data set, and then we basically fine-tune different models. As you can see, we tried GPT-4o, we tried GPT 3.5 and Llama and things like that. So there are some things. I think there's a bit of an older comparison. We haven't tried the newer models. That is something that we want to experiment with, the newer reasoning models. But as you can see, fine-tuning kind of improves the accuracy in most of these models, and fine-tuned GPT 3.5 is actually closer to GPT 4o. But GPT 4o still outperformed other base and fine-tuned models. But the advantage of fine-tuning is that we can achieve similar accuracy with less cost by using the fine-tuned GPT 3.5 turbo model, right? As you can see on the left side, there's a pricing for Llama and Llama 3.5 and GPT. If you compare the cost for fine-tuned model versus the GPT-4o model, we were able to achieve the same accuracy with lower cost by fine-tuning other less accurate models, right? So finally, so these are some examples of how the fine-tuning, how the matching looks like, right? So this is an example where we had from a CVE, this was the library that was extracted using an LLM, and then we used vector search. It gave that these 4 libraries are the most similar to that. But again, when we asked LLM, prompted another LLM to say, okay, now I have this library and these similar libraries, which among these are vulnerable, right? So it, as you can see, it actually eliminated this libconf24 and only says that this and this are vulnerable. Maybe these are not related at all, even though they look semantically similar to this, but they might be different libraries altogether, right? So similarly here, this is interesting because if there is a vulnerability in bzip3, it says these are all related packages, gzip, unzip, and all that stuff, but it says none of them are vulnerable, right? There's only vulnerability in bzip3, but bzip2 is not vulnerable. And yeah, so that's how we are basically using LLMs and vector search. First, we are using LLM to extract the name, and then we are using vector search to get the similar packages, and then we are using another LLM to identify which among these are the vulnerable, right? So a lot of this is a manual process. Like you need a lot of security knowledge, and you need to understand all these libraries to be able to, for a human to do that, and it's a very time-consuming process. But teaching LLM to do this has automated all of these tasks, right? And it's very interesting. We were able to get very good accuracy for these as well, right? I'll talk about that in the later slides. But this is another example. There's a CVE, and this was the description, and this is the product, and this final vulnerable packages. This is what we are kind of trying to achieve out of using this. So how do we score? Now that we have, for a particular library, we know which are, we know that for a particular CVE, we know what libraries are in our infrastructure, and then that are affected by the CVE, right? First, we identify all the services it is present in. Like there could be some DBR services. DBR is the Databricks runtime services, right? If it affects DBR services, then it's very critical. Universe is basically other kind of services. Maybe that is not that critical, right? So we, based on how many services that is present in this, where we use Trivy and Qualys to scan our internal infrastructure to find out which services that library is present in. So once we know all the services, we use a weighted scoring mechanism to give a component score for each CV. So over here, as you can see, there's mass, but these are some CVEs with high score, and these are all 0.99 and stuff like that, and these are some CVEs with lower score. The other kind of scoring we use is topic modeling, topic-based scoring, where basically topic modeling is an approach where if you have some documents, say for example this document is talking about life sciences and genetics and things like that, right? The document can have a lot of words, right? There are specific words in the document that could relate to a topic. Like as you can see, all the ones that are in pink over here, maybe you can't read it, but they are like life, survive, organism. These are all related to a topic like life sciences. And there is number, computer analysis, all the blue ones, they belong to a topic like computation. Sorry. And there is gene, sequence, genome, these all belong to a topic like genetics. So what topic modeling does is, basically given a document, you can identify the topics in the document, and then each document can be represented as a distribution of topics. So so for example, this document can be, like you can see that it has a distribution. It can be represented as a vector of these topics, like where each topic, each value shows how much it's distributed in that particular topic, right? So how do we use that over here? Say, for example, for each of these libraries, we consider it as a document, and the services that it is present in as the words, right? So that way we actually create these document word kind of a mapping, right? Like similar to what we have seen over here, where we have a document and a list of words. In our case, a document would be each of the library, and the words would be each of the services that is present in. So based on that, we use topic modeling and kind of generate topics. So for example, there's a sample topic where you can see most of the services are Kafka-related services. This red light shows, this kind of shows the estimated frequency within the selected topic, right? So that, as you can see, most of these reds relate to Kafka. So all the Kafka services have fallen into one topic, right? So there are a lot of topics over here. As you can see, there are some topics which are more predominant versus some topics which are less predominant. So the idea over here is in topic-based scoring, what we do is we train LDA on this data set to get a set of topics, and we hand label these topics with important scores, like between 1 to 100. Some topics might be very important, like Kafka might not be very important for us, but if there's a topic with DBR services, that is very important for us, right? And then, now given a new library or a package, we basically again convert that into this topic distribution, and then see which topic it falls under, and then give that library that score, right? And the topic score would be the library score. And there's a third type of scoring that we use as a severity score. Severity score is the score that we are getting from the world, right? Like as I said, there are these CVEs that are important to the world, and we get those scores from those databases, the CVSS score, EPSS score, and exploitability score. So we also take this score into consideration, and we do a weighted average of this score. So there are three different scores, as I mentioned. One is topic score, one is severity score, and the first score that we talked about is the product-based scoring, right? Like what services it's present in and things like that, right? So based on using all these scores, all these three types of scores, we are basically looking at this intersection, right? The ones which have high topic score, high severity score, as well as high component score, like so those are the ones that are important to the world as well as important to the Databricks. So we backtested these on 75 tickets, and we saw that the pipeline, we had like 83% true positive rate. And say some of these CVEs, like as you can see the CVE, we were able to detect 5 days prior to blog, and like it became very popular after 5 days after we detected, right? So people started talking about it's a Git vulnerability. Basically it's a bug. If you install some Git repo, it was cloning all those directories, and there's there's malicious code being executed, right? So people were actually talking about it on Twitter, but we were able to discover 5 days before it became popular on Twitter, because we're ingesting all this data as well, right? So that way it was we got an early trigger. And there was also some vulnerability in MLflow. MLflow is one of the product of Databricks as well, and we were able to detect hours before customers were talking about it, right? There's a vulnerability and things like that. And there's also OpenSSH vulnerability. We were able to detect that, and it became a security incident, and we had to patch it immediately and things like that. So we also have kind of a dashboard where we track the various scores, how many tickets we reviewed, what is the true positive rate, what is the false positive rate, and which are the CVEs that we are analyzed, and all the distribution of the scores for those CVEs, right? Yeah, I guess just a bit early. Yeah, that was my last slide. Any questions?
I'll ask you a question. Are you doing anything to associate probability or exploitability with severity? So I can explain.
So we are using the exploitability score as a feature for
VSS score as a feature?
yeah.
Okay.
So that's where, like over here, if you see, yeah, this is one of the features that we use to calculate the component score.
And are you also adding CHEP to that?
Sorry, what is that?
CHEP? CHEP is a non-exploitability vulnerability separate table that's actually published by CISA.
Oh, I see. Okay. I guess we're not using that right now. Yeah.
I'm curious if so, and I recognize that this would require a lot of legwork, but is there anything to account for? So there's a CVE, there's a vulnerable package.
Yeah.
You're using that vulnerable package, but the vulnerability might be in a function that you're not calling in your software at all. Is there anything to account for that, or it's we have this vulnerable package, we're assuming we're vulnerable to this exploit?
Yeah, it's, say for example, it's not just us, even our customers, right? Like customers can use our thing. So it's, say for example, MLflow is something that is used by all of our customers. So we want to make sure that we patch those vulnerabilities before our customers tell us. Yeah. Yeah.
Are you able to tune the model for CVEs that are inappropriately configured or placed? For example, there's some older CVEs that say they're associated with like an Apple product, but they're really associated with their Linux product or things like that. Like, are you able to tune those out of the model so it knows that they're false positives?
So, like I said, right, we are only looking at the ones that are relevant to our infrastructure. That's where we map the CVEs to our services, right? Which services does it affect? Like we extract the library from that. So what we have seen is there was a Tesla CVE, right? That is only related to like Tesla cars, where it's published and it is there in the input data. We don't want to prioritize that. So this model actually does not, like we have seen that all those vulnerabilities are not prioritized.
So there's, and you may not have run across it. There are certain circumstances where you may have like a Linux system and it says, hey, you've got a Linux CVE. But when you actually review the CVE is actually associated with like an Apple product because of how the CVE was created. So CVEs are created by giving like a placeholder for it, and if that placeholder is removed, sometimes that description is not removed, and then it's associated with a different product. There are not very many, but there's a few edge cases where that happens,
Got it.
where then the CVE you think you're reporting on is actually not accurate.
I see. Okay. Yeah, we haven't seen that cases in this model at least. Maybe it would have already filtered it for us, but we haven't seen, I mean, that would have come up as a false positive for us, but we didn't see that in our results. Yeah. Any other questions? If not, thank you.